Hey, what is up, my killers? Or not killers, actually livers, or livers, because we're going to be talking about fetuses today. Yes, fetuses. It's January 24th, Monday, 2022. I said that in reverse order, but that's just because I'm excited to be talking about fetal hemoglobin. Before I continue, my two seconds of personal discussion is that today I discovered this week something really cool: oat milk, not oat milk, coconut milk mixed with cold brew and a few packets of stevia is amazing. I should have discovered this a long time ago, but oh well, you live and you learn. But yeah, I mean, it's healthy. Relatively, like caffeine. I have to actually learn about caffeine binding. I might do that next as a part of my bio studies. But the caffeine from the cold brew is there, but it keeps me up. And the coconut milk is healthy, a little fatty, I assume. And the stevia is also, I assume, healthier than sugar. So I mix those together, and then I get a really good morning coffee kind of meal. Just wakes me up, and so I don't have to put whipped cream in cold brew like I've been doing the last few weeks, which is no good for you. And this way I can also stay vegan. I'm slowly moving the components of my meals into veganism. And which I have my weekday lunch and my weekday breakfast almost completely done, and this kind of rounds that out. So yeah, that's basically my little update for the day, personal update. So let's get to fetal hemoglobin, because that's what you really want to hear about, I think. So we talked about hemoglobin before, and there's a difference between an adult's hemoglobin and a fetus's hemoglobin. So if you look at hemoglobin, right? I guess that's the ancient English way of pronouncing it. The hemoglobin molecule here that you're familiar with has two beta subunits and two alpha subunits, beta globulins and alpha globulins. And these beta and alpha globulins actually, in their central region, right? I think you can find it in this central region here, have, and it's not pictured really here, but they have a special area of positive charge, which is caused essentially by amino acids that are on each of these side chains. So you don't see the actual amino acids here, you just see kind of the overall shape of the alpha and beta subunit chains here, but there are histidine and lysine amino acids as a part of these side chains, which these histidine and lysine amino acids create like a pocket of positive charge, because those are positively charged hemoglobin. Okay, so essentially what happens is we have to learn everything about hemoglobin, so this is one very important thing, and it's mostly important as it relates to, we learned about we learned about oxygen binding to the iron atom, the distal histidines in the heme group, which are like these little planet things right here, and we learned about the stabilization of the tense state hemoglobin that diatomic oxygen provides to the hemoglobin and turns it into the relaxed state. Okay, so just recalling all that, this positive pocket of space caused by these amino acids is actually one of the reasons that the hemoglobin molecule, macromolecular complex, is unstable to begin with. Okay, so I mean, the molecules themselves, you can think of the alpha and beta subunits being bound to each other by ionic bonds and hydrogen bonds all over the place, right? And wrapped together, etc. But in the center of the hemoglobin group, there you can think of it as there's a tension caused by the repulsion of this positive energy, positively charged region here. So what happens? Well, time to introduce a new molecule into the works called 2,3-Bpg. And so it's 2,3-bisphosphoglycerate. This molecule comes along sometimes in especially low oxygen situations when oxygen isn't present, and it stabilizes the heme group. It stabilizes the hemoglobin by fitting nicely into the center of the hemoglobin. So if you look at this diagram right here, you have the 2,3-bisphosphoglycerate molecule, which is a pretty simple molecule overall. I mean, honestly, no molecules are really quantum mechanically simple, other than maybe a hydrogen atom. But you see here, this 2,3-Bpg fits within this positive pocket of hemoglobin. And what this does, this 2,3-Bpg, it has two phosphates on it. And these two phosphates contribute, and this is the glycerol group right here, OH, carbonyl O, and O. This contributes a large negative charge due to the phosphates. And so what happens is the positive charge is here, and this negatively charged molecule comes by, and it fits very nicely into the center of this hemoglobin, specifically because mostly due to the amino acids on the beta globulin subunits here. So these amino acids, different lysines and histidines, they're labeled 82, 143, 1 and 2. They and you could, 1 and 2 are at the beginning, I guess, when they start counting the chain. So they bind to the different parts of this 2,3-Bpg, this phosphoglycerate, and keep it there. And what happens is, when that happens, then this 2,3-Bpg, this entire hemoglobin molecule becomes stabilized. Okay, so it becomes effectively in the relaxed state, and therefore, when it's in that state, then it doesn't. It lets go of it's stable, so it doesn't need to hold on to the O2 as tightly. Okay, now, what consequence does that have for hemoglobin? Why did I bring up fetal hemoglobin? So, fetal hemoglobin is different than adult hemoglobin. Fetal hemoglobin actually has 2 gamma subunits rather than 2 beta subunits. And what's the difference between these 2 gamma and 2 beta subunits? By the way, I should take a quick note. These are the most common forms of hemoglobin. There are actually other forms of hemoglobin in the body. But we're talking about for adults and fetuses, respectively, the alpha adult hemoglobin, HbA and HbF. These are the most common kinds. So I wanted to throw that in there. But going back to the gamma, the structure of the fetal hemoglobin. Fetal hemoglobin has 2 gamma chains, so 2 gamma globulins instead of 2 beta globulins. And these 2 gamma globulins, let's see if I can find a good picture. These 2 gamma globulins, the issue is with these is that they actually have, gamma globulin has, instead of histidine as one of its amino acids in its central pocket, it has it's replaced with serine. So why is that different? Because otherwise it's mostly the same molecule, and it's up with some conformational differences. So the reason that is important is because serine is not negatively charged, it's neutrally charged. And what does that mean? If it's neutrally charged, then this pocket here, right, this pocket at the center of the hemoglobin will be much smaller by consequence, right? Because there won't be as much repulsion in the pocket. Now we're getting into electrostatics, which is super interesting. Whenever we get to protein electrostatics, it's really interesting to me because it reminds me about physics in general, right? Like physics is very integral to everything, but sometimes you forget about it when looking at like the biochemical level. But anyway, so 2,3-Bpg, right, can no longer fit within this pocket. So it's one thing you might be asking, and this comes down to protein enzymatics, conformational attraction physics and whatnot, but 2,3-Bpg can no longer fit into this pocket, and other molecules cannot either. So this pocket, it will pretty much this fetal hemoglobin will be unstable because it no longer has a stabilizing agent. So in order to stabilize, what does it have to do? It has to hold on to oxygen much more tightly. Okay, oxygen is going to be present. And that's important because the mother with her standard adult hemoglobin can disassociate from oxygen more easily because there's the 2,3 Bpg stability occurring. But a fetus a fetus has more blood, more hematocrit, right, than a mother, more red blood cell material, and thus more hemoglobin, actually has to hold on to oxygen more tightly, because that's important, because the oxygen binding curves, right, if you remember, it all comes down to the survival of the fetus, and of the adult also comes down to the oxygen binding curves. So basically, a fetal hemoglobin oxygen binding curve is this blue curve here. Adult hemoglobin oxygen binding curve is this red curve here. The fetal hemoglobin at 50%, notice this area here. This region here is the region at which 50% of the oxygen available is saturated. It saturates the hemoglobin, and remember, the oxygen binding curves are graphed in accordance with the partial pressure of oxygen. For example, in the lungs, and the partial pressure of oxygen in the lungs is about 104 under normal circumstances millimeters Hg, and that's at almost 98% saturation. Around 50% saturation for the adult hemoglobin. You have it occurs at 26.8% partial pressure, but for the fetal hemoglobin, it takes a noticeably lower partial pressure to saturate oxygen, to saturate 50% of the oxygen to the hemoglobin available. Because remember, we're dealing with fetal hemoglobin here, which has a much higher oxygen binding affinity. That means it's going to grab onto that 50% of the oxygen at a lot lower oxygen pressure, right? Oxygen pressure just means the amount of partial pressure of the gas, of the oxygen gas, which is bombarding the hemoglobin molecule. So at that point, that's why the fetus has this situation going on. So at that point, the fetus can hold on to this oxygen, and I guess the fetus will be able to deliver this oxygen also effectively, but also it needs to hold on. It's not giving it to anybody. The mother, through the umbilical tube, is supplying oxygen to the fetus, but the fetus, it needs to use the oxygen to grow its own tissues. So anyway, that's a quick precursor on that. One thing I do want to mention is 2,3 Bpg, right, is a molecule. So there's other reasons why 2,3 Bpg is important as a stabilizer between the T and R states for hemoglobin, and that is when oxygen is not present within a body due to hypoxia, low oxygen content of your blood, of your lungs, wherever. And the reason could be several. There could be several reasons. One of them is anemia. You could have less iron available in your blood, and therefore you could have less heme, and therefore you could bind less oxygen. So in order to essentially stabilize in the same way a fetus's hemoglobin is stabilized by 2,3 Bpg, which binds oxygen more tightly at that point, or at a much lower partial pressure. The same thing is done when you are anemic and don't have enough iron. The binding of oxygen is made much stronger at a lower partial pressure by the presence of 2,3 Bpg. So assuming there will be some sort of synthesis pathway that occurs in that situation. Also, if you're at a high altitude and there's less oxygen available, you need to grab up that oxygen that is available faster, so that there'll be higher amount of 2,3 Bpg in your system. And then also if you have lung disease of some kind, so if you have pleural effusion or something, and you have fluid leaking into your lungs, then at that point there'll be less lung capacity, so there'll be the hemoglobin that's present there and to travel to the rest of your blood needs to be able to grab up the oxygen faster, so therefore the 2,3 Bpg content will be higher. So that was a quick detour into fetal hemoglobin versus adult hemoglobin. I find it very interesting, and thanks for listening. I will see you guys later.